Welcome again for our next talk in the series by Sergio. So he will talk on ideals of contractible DGAs. So yeah, over to you, Sergio.
Thank you very much. Before reaching these ideas of contractible algebras, I'd like to review some basic notions we saw earlier on coarse geometry. Please interrupt me anytime if the audio is not clear or there is any other question, problem. So a reminder, we were looking at groups and we wanted a structure. We wanted a structure on a set that encodes the large-scale geometry. So I remember here the coarse structure is a family of binary relations, so subsets of S squared, which satisfies certain properties. If a relation is controlled, then every subset should also be controlled. Then the union of two controlled relations is also controlled. So these are properties that relate to a filter structure. So you could say that this, together with non-emptiness, this is a filter. It's a filter of, sorry, not a filter, an ideal. Yeah, the dual notion. That's wrong. Yeah? It's an ideal structure. Yeah. And then we also have properties that relate to the groupoid structure of x times x. So remember that x times x has a groupoid structure, which is called the groupoid structure, where the composition of xy with yz is just a pair xz. So there are properties that relate to this groupoid structure, and it is that all units, so the set of all units is controlled. So this is the diagonal. And then the structure is closed under compositions and taking inverses. So we had seen this. Then a coarse space is just a set endowed with a coarse structure. Okay, so we had also seen some examples. First one, which is an extension of what we saw for geometric group theory, is the bounded metric structure. So essentially, a relation on X is controlled when the distance is uniformly bounded on this relation. The distance is uniformly bounded. Then I did a terrible job explaining the C0 core structure, so I will stop here a bit more to account for that. Now, if again, to a metric space, we can associate a different core structure. This is called the C0 core structure. And this C0 here means tending to 0 at infinity. Why? Well, because the control sets, again, are those for which the distance function tends to 0 at infinity. So that's this condition here. For every epsilon, there is some compact set, and outside of the square of this compact set, then the distance function is less than epsilon. We had seen some examples. So first example, we can draw easily this open interval, and then, okay, so then the control sets or the relations are subset of the square. So here are some examples. This is definitely controlled, right? Because it's actually contained in a product of compact sets. So the condition there is trivially satisfied then. This is also controlled, but because of a different reason. The reason being, no matter how small I consider epsilon, so how small this uniform neighborhood of the diagonal is, eventually here meaning outside of a compact set, eventually E will be contained in that uniform neighborhood of the diagonal. This is not the case here. If I choose this uniform neighborhood of the diagonal, no matter how big I choose my compact set, there will always be something escaping this compact set which is not in the neighborhood of the diagonal. We have a problem here and here, right? And same here, we have a problem there, and here the problem is that this seems close to the diagonal, but if I choose my uniform neighborhood very, very thin, then again it will be outside. Okay? I hope that with this, the C0 core structure is more clear. And there was a question, which is a very good question. My drawings were wrongly suggesting that, we had examples of controlled subsets of the plane, and they were bounded. So the question was, is this the case? Is being bounded equivalent to being controlled? And the answer is no. Certainly, if now I will deal with the real line. So now my metric space is the real line with the standard metric. And certainly every bounded subset of the plane will be a controlled relation because it will be contained in some product of compact sets. Okay? But this is not equivalent to being controlled. Here we have an example. So the example here, we consider this region E, which is the blue one. So the blue region is E together with this inner part here. This is also, no, this here is also E, and over here as well. And this one is definitely not bounded, but it is controlled, right? Because no matter how small I choose this epsilon right here, this epsilon, no matter how thin this uniform neighborhood of the diagonal is, I can always find a big enough product of compact sets. So that would be this square here. This square would be k times k, and outside of it is contained in this uniform neighborhood of the diagonal. So this would be an example of a non-bounded controlled subset. So far, before we move on, are there any questions or comments? Okay. Yeah. We had also seen another example, and it was the topological coarse structure associated to a compactification. So if we have this paracompactness is a technical assumption, we can ignore this now. Here's the important part: locally compact Hausdorff space. Then for every there are compactifications, and to every compactification you can associate a core structure. So again, if you remember, a relation is controlled if when you take the closure inside the product of the compactifications, then this only touches the corona in the diagonal. This only can touch the corona of the square in the diagonal. We had also seen one example. Okay, so that's a quick review. So far, no questions. So then let's move on. So now we will define the notion of connectedness, but from far away. So as we have connected components, path-connected components in topological spaces, here we have something that we call coarsely connected components. So essentially, these are subsets these are maximal subsets which are connected from far away, from infinitely far away. So given any coarse space, I will define a binary relation there. So for every pair of points, I will say that they are in the same coarsely connected component, they are in the same component, if and only if, if and only if, the idea here is that they are at finite distance. Okay, so the idea is that the distance between those points is finite. So there exists some control set such that the pair xy belongs to E. Now, if you remember, again, coarse structures are closed under subsets. And so this condition is actually equivalent to the following one. So the relation whose only pair is xy is controlled. Okay, so these two conditions are equivalent. You can prove that this is an equivalence relation, is an equivalence relation, and the equivalence classes for this relation are the coarsely connected components. So the coarsely connected components, again, are the equivalence classes. The equivalence classes under this relation. And a space, so a space X is coarsely connected if it is empty or there is only one connected component. So we can summarize that saying it is coarsely connected if there is at most one coarsely connected component. Coarsely connected component. All right? So again, the idea here was that 2 points are in the same component if the distance between them is finite. So let's see some example. You might have come across this notion of extended metric spaces. So an extended metric space, it's basically the same as a metric space, but we are allowed to have points at infinite distance. This distance can take the value infinity. Okay, so one example where this appears is the extended real line, something you use for measure theory. So if you study analysis, integration, measure theory, you will very likely come across this space, right? So you add 2 points at infinity, and then, yeah, the distance between minus infinity to every other point is infinity whenever x is different from minus infinity, and same for infinity. Okay, so when then again, you can still use this bounded metric coarse structure, and then we endow it with the bounded, the first example that we saw, the bounded metric coarse structure. Satisfies the following. So 2 points are related, are in the same coarsely connected component, if and only if the distance between them is finite. Why? Well, again, if you look at the definition here, they're in the same component if and only if the set consisting of this pair is controlled, which means that the supremum of distances on pairs of this set is finite, but that supremum is just this number here, okay? So that's why. And this means that xt is coarsely connected if and only if all distances are finite. So all distances are finite. So then this means that actually xt is a true metric space. It's a metric space. Yeah. So here you have one example already. This extended real line, this would be an extended metric space, and it has three coarsely connected components. So minus infinity, the real line itself, and plus infinity. Which means that from a coarse geometry point of view, this is a disjoint union of spaces which have nothing to do with each other. Okay, so the idea here is that these are so separated that they have nothing to do with each other. You know, if we study topology, then this is very close to the real line. These are limit points of the real line, but in coarse geometry, they are separate. They have nothing to do. Another example can happen with graphs. So if you remember, to every graph, we can associate a metric space. Now, if the graph is not connected, this will actually be an extended metric space. So the distance between 2 points, 2 vertices, so is my vertex set. Here are the edges of the graph, and the distance between 2 points is the infimum of the lengths of all paths joining them. So if x and y are in the same connected component of the graph, then this is the usual notion of distance. Otherwise, yeah, what happens if x and y are not in the same connected component of the graph, then the distance between them is infinite. Then this infimum is taken in 0 infinity, right? So then the distance between them, well, is the infimum of the empty set. There is no path from x to y, which means we're taking the infimum of the empty set. So it's the greatest lower bound of the empty set in this space, which means this is infinite. Okay, so in general, to any graph, there is an extended metric space, and then it turns out that BD, so this extended metric space, is coarsely connected. We know that this is equivalent to Bn. We already know that this is equivalent to dVn and a real metric, Bn a metric. And this is equivalent to the graph Bn connected. Okay, it's a graph, this has to be connected. Yeah. Okay. Let's see maybe one visual example. So we can consider a graph as follows. It's going to be the disjoint union of these 3 graphs here. So each of these is connected. We have one piece here which is connected and unbounded. There is another bounded connected component here, and this is a bounded connected component. So as a coarse space, this graph has three connected components. So this graph has three coarsely connected components. Which are the components of the graph. One of them is unbounded, and the other one is bounded. The other ones are bounded. Yeah. Okay. When we were studying geometric group theory, the Cayley graph was always connected, so we didn't have to take infinite distances into consideration. Okay. If there's, are there any questions so far? If not, let's move on. So now I want to study, you remember this identification of maps up to closeness. We will do the same here for coarse spaces now. So my setting is the following. I have two maps, F and G, where the domain X is any set and Y is any coarse space. Then we can tell when two maps are close. So FG are close, and we will write something like this. If there exists some controlled set, so the idea is that the difference between them is controlled, but there is no way to measure here the difference, right? We have to formalize this. So if there exists some controlled set of Y, so let me be explicit here, there is some controlled set of Y such that f of x, g of x belongs to E for every x. Okay? Okay, this is equivalent to the following. So you see this set here, if I have f and g from x to y, I can define, let me have more space here, yeah. If I have these two maps, f and g from x to y, there is an induced map, f times g from x times x to y times y, which turns x1, x2 to f of x1, g of x2. And then, yeah, we can apply this map to the diagonal of x. So this would be exactly the set f of x, g of x, such that x is in x. So f and g are closed if and only if this set is controlled, meaning that it is in the coarse structure. Well, why is that? Well, because here we are saying that this set is contained in some controlled E. But again, coarse structures are closed under taking subsets, so then this one also has to be controlled. So they turn to be equivalent conditions. Yeah. Well, we have already seen one example. This is a generalization of what we already had. So again, we assume now that Y is a metric space, and we consider the bounded metric coarse structure. So I remember here, I will write it in a different way now. So these are the, yeah. Okay. Sorry about that. Okay. It's a bit laggy now. So these are the relations on X. We're working in Y. These are the relations in Y such that there exists some R for which the distance from x1 to x2 is at most r for every pair of points in E. Okay. So for this reason, now if I have two maps, F and G, then F and G are close if and only if there exists again some number such that the distance from f of x to g of x is at most r for every x. So this is a way of saying that f and g look the same from far away. They look like the same map. Okay. Some observation or remark that we have to do here is that this closeness of maps is an equivalence relation. It's an equivalence relation on the set of maps from x to y. This is an exercise that you can practice with. Okay. Now I would like to talk about bounded subsets. So let's think of the usual case for a metric space. So now V is bounded if and only if it has finite diameter. We know that, right? So V is bounded if and only if the diameter of B is finite. But here, the diameter of B is the supremum of the distances between pairs of points of B. So we can write something like this. So if you remember the definition of the coarse structure here, this is equivalent to B times V being controlled. So a subset is bounded if and only if its square is controlled. So we can now take this as a definition for coarse spaces. Okay, so that's what we will do. How is it going so far? Are there any questions? Is this too fast, too slow?
No, this is okay for me, at least.
Perfect.
So Sergio, so can you go back to the last slide? The last part.
Yeah.
Yeah, this remark.
Can you speak louder?
Yeah, fine. You can go proceed to the next.
Okay, nice. Okay, so we had this characterization of bounded sets for metric spaces, and we now can generalize it to coarse spaces. So if for a general coarse space, a subset is going to be bounded if it satisfies one of the following conditions. If it satisfies one of the following equivalent conditions. So there are 4 conditions here. All of them are equivalent, and when one of them and then all of them are satisfied, I will say that V is bounded. So the first condition, we just saw it, is that V is bounded if B times V is controlled. Okay, it mimics this idea of having finite diameter. You can also say there is some point x such that b times x is controlled. So for a metric space, this would mean like every point of B has, there is a bounded distance from points of B to X. Okay, so if we think of a metric space, it's a metric space. This condition reads there exists some R positive such that the distance from Y to X is at most R for every Y in B, which means that B is contained in the closed ball of center X and radius R. Right? So this is another characterization of being bounded. And another characterization is there is some entourage such that B is, and actually there exists some entourage, and there exists some point such that B is the E thickening of the point. This E thickening, what is it? Is the set of points which are related to X. So these are the points Y such that XY is in the relation E. This mimics the idea of being a certain subset of a ball. This mimics the idea of being a subset of a ball. And one last characterization is that this inclusion as a map is close to a constant map. Okay, so there is a point to which B is close to. B is close to a point. That's the idea here. Okay, so let's see some examples. We basically had 3 examples. First one is the bounded. So if I have a metric space, is the bounded metric structure. Then B is bounded with respect to the core structure. If and only if it is bounded in the usual sense, which I will write like this. It is bounded with respect to the metric B. Okay, so we just saw that. And more interestingly, now let's assume that X, again, it's a metric space. It's a metric space. And remember that we had this C0 coarse structure, which I will write again. So again, these are the relations for which for every epsilon, there is some compact set such that the distance on E minus k times k is less than epsilon. So what are the bounded sets here? In general, we can say the following, and now we will refine this. In general, we can say if, so let B be a subset of X. If B is bounded with respect to the core structure, then it is also going to be D-bounded. It's bounded for the metric. And if B is relatively compact, then it is bounded with respect to the core structure. So in general, we can tell the following, right? Well, the first part, why is this true? Let's call this A, let's call this B. Why is A true? So we assume that V is relatively compact, then just for every epsilon, we can choose K to be the closure of B. So then if you take B times V minus K times K, this is empty, and so this condition is clearly satisfied. Okay? So this means that B times V is controlled. I will write this down. B times V is controlled, and so B is bounded with respect to the core structure. And for V, we now assume that V is bounded with respect to the core structure. We want to prove that it is bounded for the metric. So, yeah. So we choose one, we choose any epsilon. We choose epsilon. Then, since B times P is controlled, there exists some compact set such that the distance on B times V minus K times K is less than epsilon. So I want to show that B is very close to K. So K is bounded, so B is also going to be bounded, right? So B times V minus K times K. This is B minus K times B union B times B minus K. And yeah, so if there are two cases here, if B minus K is empty, then if this is empty, then it means that B was actually inside of K, which is relatively compact. So then B is bounded. Yeah. Okay. Otherwise, we choose one point in B minus K, and then for every other point, we have that the pair xy belongs to B minus K times B. So the distance between them is at most epsilon. And this would prove that B is inside the ball of center x and radius epsilon. And then B is bounded. Okay. So if we go back to these relations here, now we can say something. If the metric space is proper, then being bounded is the same as being relatively compact. Okay, so let's write that down. Conclusion. So for if XP is a proper metric space, then actually, if and only if, right, this is an equivalence. The metric space is proper exactly when being bounded and being relatively compact are equivalent. So in this case, is bounded with respect to structure, if and only if B is bounded if and only if is relatively common. Far so good. We also have another example. There are any questions about the previous example, please? Now I will move on. So again, we consider now a complication, and we would like to understand what are the bounded structure. And remember here that coarse structure associated with this are the relations.
Sergio, your voice is breaking actually.
Is it upside down, or can you see my whiteboard?
Yeah, whiteboard is fine, but the voice is a bit
Yeah.
low.
Now the voice, is it better?
Yes.
Yeah, it's better, yeah.
Great, thank you. Okay. I hope it is more clear here.
Yeah.
Okay.
Right.
Perfect. So if you remember here, a set is controlled when if you take the closure, this is the closure in the compactification square, and then you remove x times x, then this is contained in the diagonal of the corona. Remember here that the corona of the compactification is just a remainder space. It's the set of added points. So now let's consider a bounded set. So let's consider just some subset of x. Then B is bounded. I want to understand when is B bounded. If and only if B times B is controlled, and this is equivalent to B times B intersection with, if you remember here, this was the corona of the square. I want this to be contained in the diagonal of the corona, right? And now let's compute this intersection here. Sorry, this is the closure. Yeah. So first of all, this is the same as the product of closures, right? Then we would have the following. This is the same as the closure of P intersected with the corona times the closure of B union the symmetric of this thing. Okay. So okay, so if the intersection of the closure of P with the corona is empty, then the condition is satisfied. The condition is satisfied, right? Because we have the empty set here. So B is bounded. So B is bounded. Now let's assume that this intersection is non-empty. So if the intersection is non-empty, then in particular, this closure is non-empty. And so B is non-empty. We choose now, so we can choose one point omega. We can choose one point omega in the intersection of the closure with the corona and some point y in B. And then you see what happens here. then the corona, so then omega y is a point in this monster, but it is not in the diagonal of the corona, because this point here is not in the corona, okay? So B is not bounded. So we found a very reasonable characterization, meaning that B is bounded if and only if the closure of B in the corona, the closure in the compactification, does not touch the corona. Okay, so this here means that if I take the closure of B inside the compactification, I am still inside X. Way of saying this, I take the closure of B with respect to the compactification, and this is still contained in X. Makes sense. It's a way of saying that B is not close to infinity. Okay, so far, any comments, curiosity, any question? There isn't any, then we're very close to, yeah, we're very close to understanding this course homology already. We have almost all the ingredients. So I would like to talk about maps between coarse spaces. We want this coarse homology to be a coarse invariant, so we need to find what it means. Right? So I will consider map between coarse spaces. There are several definitions going on here. Right? Let's say we're working with a category. I already defined my object, and I want to define the morphism. So a map is space. Image is y.
I guess the
Yeah.
voice is again.
No, it's still breaking.
My voice is breaking.
Yeah.
Right.
Can you hear me now?
No, it's still.
Break.
Hello.
No, it's not stable yet. No, no.
No, no.
Might be my connection. My
No, can't hear properly.
I was getting. Can you hear me clearly now?
No, it's almost same.
Was it that bad before?
What?
Was it bad, the voice before?
Sorry, can't hear you.
Yeah, the voice is not clear.
Was it clear before?
Yeah, before it was
Yes.
fine. Now, recently only.
I'm honest, I have no idea why this happened.
And now it's a bit better, I guess.
Okay, what about now?
Yeah.
Now it's perfect.
Better.
Oh, thanks. Perfect. Then let's continue.
Mm.
Okay, if I share the screen, still clear?
Yeah.
Yes.
Perfect. Okay, thank you. Okay, so we want to define the morphisms of our category of coarse spaces. Yeah? Okay, so we need some definitions. A map is controlled if it sends points which are close to points which are close in the following sense. So for every relation, for every controlled relation on X, the image is a controlled relation of Y. Okay. So in other words, so here this is the set of fx1, f of x2, such that x1, x2 belongs to E. So I'm saying that this is controlled. So in other words, f is controlled if for every controlled entourage of x, there is some controlled entourage of y, such that if x1, x2 is in E, then the image fx1, fx2 is in F. So this is a controlled map. Okay. So if you apply this definition to geometric group theory, to discrete groups, then this is equivalent to being a quasi-Lipschitz map. It's an analog of being Lipschitz. Now a map is proper, F is proper, if for every bounded set of Y, the pre-image is bounded in X. So if you remember before, we saw an example where bounded and relatively compact are equivalent. So in some examples, you recover the usual notion of properness of topology, right? So in topology, a map is proper if the preimage of compact sets are compact. And yeah, in some cases, you will recover that as a particular example. Okay, so then a map F is coarse, is a coarse map, is a coarse map if it is both controlled and proper. So this is our category. The coarse category has as objects coarse spaces. And as morphisms, so a morphism, let me actually write a morphism from X to Y is a coarse map from X to Y. Okay, and yeah, if you want to make sense out of this, then you have to prove that the identity is a coarse map, the composition of coarse maps is coarse, and yeah. So composition of coarse maps is coarse. I hope that my voice is not breaking here.
No, it's perfect.
Thank you. And okay, so now I want to compare this with topology. So let's imagine some line here. We now have this category of coarse spaces, and we want to compare this with topology. So for here, the objects are coarse spaces, and we have controlled proper maps as morphisms. And here we had topological spaces and continuous maps. Morphisms. Well, we introduced a notion of homotopy between two maps here. So if I have two maps now from X to Y, there is a notion of homotopy defined between them, and then there is a quotient category. So there is topological spaces up to homotopy. Let me separate this here. Yeah, let me separate this. Yeah. And so now in this quotient category, the objects are the same, topological spaces, but a morphism, so a morphism between X and Y is an equivalence class of continuous maps, all the equivalence classes of continuous maps from X to Y. So this is the equivalence class under homotopy. And the interesting part here is that we can do something very similar for coarse spaces. We can consider now maps up to closeness. So for that, you need to show that this closeness relation is compatible with composition. So if F1 is close to F2 and G2 is close to G1 is close to G2, then if these arrows can be composed, then we have this relation between them. Right? So you can define this quotient category where objects are coarse spaces. And again, the morphisms from X to Y are now the equivalence classes of coarse maps. Up to closeness. I will finish very quickly with what a coarse invariant is then. So in topology, something was said to be a, if I have functor from topological spaces to some other category, then this functor was said to be a homotopy invariant if you can factor this functor through quotient category. There is some factorization. We will tell the same here. These are homotopy invariants. And the same goes here. So a coarse invariant, a functor from the coarse category to any other category D, is a coarse invariant if you can factor it through this quotient category. Are the coarse invariant. For the next occasion, we will introduce coarse-cohomology, and we will comment on how this is a coarse invariant. So what is the advantage of a coarse invariant here? The advantage is that coarse invariant and two spaces are coarsely equivalent. So they are isomorphic. And they have the same. The text is isomorphic I will stop here because of the time and allow for time questions.
Hi, Sergio. So I have just a few query and just on the go. I could not figure out some of those. So where you defined first the coarsely connected thing, like 2 points are coarsely connected. So there you said two condition are equivalent. Like is that immediately follows something? Like I could not follow that part.
Let me go back.
Uh,
The voice is also cracking for me, so there
okay.
is
Uh,
you were
yeah, this
saying, yeah,
part. Yeah,
about
yeah.
this. Yeah.
These two equivalent thing like there exist in control sets is that xy belongs to the control set is
Mm-hmm.
equivalent to the singleton set is controlled. Like, is
Yes.
that something immediate from the property of the control system or something?
Yes. Let's repeat it. Yes. So if this happens, so let's go from here to here, right?
Yeah,
So
that's
let's do
the
this.
other side is fine.
Okay. So this arrow is clear.
No, this one is on the I think the problem. The other side is fine.
Okay.
If the
So then
singleton set is controlled, then that is the E set I can take.
exactly. So for that, exactly as you say, you just take this E, right? And now
Yeah.
we assume that this E exists, and we define F as this singleton.
Yes.
So this is a subset of X times X, and because of this, F is contained in E. And there was one axiom that says that the core structure is closed under
Oh,
subset.
I see. Correct. Right. Yeah.
Right? So if I was to go back to the axioms,
Yeah, that I remember, right.
exactly this is the one we're using here.
Right. Yeah, right. Okay. And
Yeah.
so for the discussion, like whatever you example you gave, it seems like if I have a metric space and with the induced code structure from the metric, then almost the connectedness and boundedness all seems to be the same with respect to the code structure as well as the standard metric. Like if it is connected in the metric space, then it is connected like coarsely connected as well, and similar for the boundedness as well. Like is that true or I'm missing something? Like there is some
Um,
example where one pair could be connected, in other case it is not.
Apologies because I will have to make you repeat the question as I
Yes,
don't.
sure. So I'm
So
saying that
yeah.
for the suppose you have a metric space x comma d,
Mhm. That I
then
got it.
then you consider the code structure induced by this D, like your
The
epsilon
bounded
D.
metric structure, right?
Yeah,
Mm-hmm.
that
Mm-hmm.
epsilon D. Then in this, like here in the with respect to this code structure, if I consider any connected, like the connectedness, I'm saying connectedness or boundedness in this code structure is equivalent to the connectedness and bounded in the original metric space. Like, is that true? Or
I see. I see. So we have two notions here: connectedness
yeah,
and boundedness.
right.
I will answer the second one first because it's a bit easier. So for boundedness, a subset V of X is bounded with respect to the core structure if and only if B times V is controlled, right?
Right.
But this means, again, that there exists some R such that the distance between x1 and x2 is at most R for every x1, x2 in B times V.
Right.
But this is a way of saying that the diameter of
Yeah.
B
B is
is at most
right.
R. So then, I mean, well, there exists some R such that, yeah, and this is the same as BBM bounded
Right.
with respect to the metric. So one answer is yes, boundedness is the same with respect to this coarse structure and with respect to the metric.
Right. And
Right? So now let's go for this one, this other question. So what is, this is coarse connectedness. So we will compare coarse connectedness versus connectedness. So yeah, if there are some relations, but they're very different things versus path connectedness and versus connectedness. So first, the space.
yeah, maybe just path connectedness. Yeah, if that those are related. Yeah.
So this space is coarsely connected. If and only if all distances are finite. Yeah. Is this clear, or should we?
Right. That's fine. That's due to the equivalence condition you have, right? Like x
So
singleton xy belongs to the contour set, which means distance has to be finite.
perfect. Exactly. So also something I didn't say, a space is coarsely connected if and only if the union of any two bounded set is bounded, and this is true for metric spaces, right? So as long as all distances are finite, then this is coarsely connected. Now, path connectedness. Path connectedness implies coarsely connected. This is something you can prove using the Heine-Cantor theorem, right? But there is no way back. And we already have an example with finite generated groups. Example given, this finite generated group. So for example, the space set with the usual metric is coarsely connected. All distances are finite, but it is not path connected. And now, if you want to relate this to the usual connectedness, then this is the usual thing in topology.
Right.
Yes.
And
did I understand your question, or?
yeah. That's what I want to do. Yeah. And just for the like, I just got this because in the graph setting, it was already like the same thing, right? For the graph, you define the distance to be the length of the minimum of the edge joining those 2 points. Then there, the connectedness is exactly same as the normal connectedness, right?
Oh, that's a very good question. So for the graph, for the Cayley graph, we associated this metric space, which is not path connected in general, not path connected, but it is coarsely equivalent or quasi-isometric to a space which is path connected. But this is coarsely equivalent or quasi-isometric to the geometric realization of the Cayley graph, which is path connected.
Okay.
you can ask now, this raises the question, given a coarsely connected coarsely connected metric space. I mean, just a metric space, right? Where all distances are finite. Given a metric space, which is then coarsely connected, is there path connected metric space y such that x is equivalent to y? So is this aligned with the question that you had in mind?
Yeah, right.
Let me think of the following example here. So as a subset of the real line with the induced metric, with the inherited metric, this is coarsely connected. It's a coarsely connected metric space. Exactly. It is not transitive. There is a notion we're not explaining here, which is satisfied by path-connected metric spaces and invariant under isometries, quasi-isometries. So yeah, there is something called transitivity. Yeah, then X is not coarsely equivalent to a path-connected metric space because it is not transitive.
Right.
And what is this transitivity? X. It is because X is not, let's say, are connected for any R. So here, what does this mean? A space Y is R connected if for every pair of points, in Y, there is a path x0 starting in x, x1, 2, 2, 2, xn, finishing at Y, in Y, such that any two consecutive points have distance at mod R. So you can see that this is not the case here. Okay, so I'm considering all powers of 2. So yeah, 0. So I'm considering 1, 2, 4. No matter how big I choose this R, the space is never going to be R connected. And for this reason, you cannot find a path connected metric space which is equivalent to it. It's a very interesting question. Yeah, and you come across with weird examples of these pathological spaces.
Right. Okay, so one last one, since you said in the maybe you will discuss in the next one, but just curious, what's the model structure on your on the course spaces, what you defined a category on that category, there is also similar kind of model structure, like the equivalence relation. I can think of the equivalence close relation you defined. And for the fibration and cofibration, like are those the same notion that we used for the standard topological space, or there are some other notion for those?
I'd love to know. That's a very nice question. So yeah, in topological spaces, we have these theories of model structures, right? Where we have
Yeah,
weak equivalences,
yeah,
vibrations, and cofibration.
right.
Um, well, I should rather have it there,
Yeah,
right?
yeah, upstairs. Yeah.
Maybe up here. So for coarse spaces, we have weak equivalences.
Right.
That's very clear, just the coarse equivalences.
Mm-hmm.
So at least we already have some structure which is weaker than a model structure, which is this is called a category with equivalences.
Mm-hmm.
Category with weak equivalences. Now a question is, what is the best or the most reasonable? What does it make sense here to choose as vibration and cofibrations?
Right.
As far
Even
as I
like
know, yeah.
one possible choice of vibration and like the trivial cofibration is good enough to generate the model structure. Like at least one category is fine. Like one choice of vibration or cofibration is enough to guarantee the model structure. Comfortable with that.
Exactly. You want to say here, like, if you determine one of these classes, the
Yeah,
other
yeah,
one is
yeah.
determined.
Other
Yeah,
than yeah, you can
exactly.
determine that.
So this, I don't know. As far as I've looked into this question, which is also very interesting to me, there is no consensus or nothing that is agreed upon on what is the best choice of this class of cofibrations and vibrations. I'd love to know. Yeah,
Uh-huh. Okay, okay, okay.
it's a very nice question. It's on research. Yeah.
Uh-huh. So another another just like query kind of thing. So if I have a map from X to Y and on X, like I have a code structure, then can we give a code structure on Y? Like the trivial one, full X cross X is fine, like all possible subset of X cross X. If I define that, then any map will be coarse map, right?
Oh, yeah. This is a topological category, right? So
Yeah,
yes.
so I'm saying like on the target space, like on Y, if I consider my code structure to be all possible subset of X cross X, like every set is controlled basically,
So
then any map is control map, right?
just a moment. You have a map from X to Y, and you only have a core structure in one of them, right?
Yeah, yeah. That
Which
yeah.
which one do you want
On
to
the
start with?
on Y, maybe just the trivial one, like P of X cross X power set.
P of XX. That's
Yeah, sorry, Y. It's on the
yeah.
Y side.
Sorry. Yeah, my bad. Um, so this is the maximal core structure, and then Y is bounded.
Right.
So then this map F is going to be controlled for every choice of a core structure.
Yeah.
Yeah,
True, right?
yeah.
Like
It
coarse
is
map probably will not hold, right? Uh, is that coarse map
exactly.
as well?
Properness
Uh,
can be a problem. F is
right.
proper if and only if. Um, so you have to send the preimage of Y has to be bounded. So if and only if. this coarse space is bounded.
Yeah, this is bounded, right?
If and only if this is also the maximal structure, but on X. Right. So sometimes for these categorical constructions, you might be interested in only looking at control maps. And if you do so there is this control category where objects are still coarse spaces and morphisms are just control maps between them. And if you do that, then this becomes a topological category in the sense that there are initial and final structures, right? So if you have a collection of maps from a set to a collection of coarse structures, so this is called an U source, then there is a initial coarse structure. The initial coarse structure in X would be the largest coarse structure on X such that every Fi is controlled. So this is very similar in topology. In topology, you could have something like the initial topology, which is the smallest topology for which the maps are continuous.
Right, exactly. Right.
Yeah.
Thank you. So
Yeah, thanks for your question.
So if anyone else have any question or okay, others people relate, okay. So okay. Okay. So that's all I think also Sachin also left somehow. Okay. So let's stop here then. We'll meet next week then at the same time.
Okay, so thank you very much for your
Thanks.
attention here.
Yeah. Okay. Bye then. See you.
Next week.
Yeah.